Greetings, everybody. This is our sixth week of lectures on video. And as you recall, we had a short week because we had a snowstorm and had only the class on Wednesday. So in this video, I'm going to talk about the microcode example that we covered, and then also talk a little bit about the connection between the machine and the micro layers of VESP, as there is a homework assignment that uh, relates to that subject matter. So the microcode that we wanted to generate was about this machine operation here, which is basically a conditional statement that sets the value of ix to ix plus 5 when a is equal to 0, and a is actually the accumulator or the a register of our VESP. Otherwise, it decrements ix by 4 and then sets it to back to ix, returns that value to ix. So in order to convert this into a microcode, we rephrase it by saying that if a is equal to 0, branch to the location to add 5 to ix. That is to say, branch to a place where this addition will take place. Let me just actually write it that way so it's a little more clear, where 5 is added to and then otherwise we subtract 4 from ix. So this rephrasing of the statement here kind of like makes it a little more precise as to what we really want to do in the microcode itself, because it gives us the two directions that we might fall upon based on this condition of a being equal to 0 or not. So so the first thing that we then do is to write a micro instruction that allows us to branch to this place when a is equal to 0. The place that we want to branch to, of course, is not determined yet or determinable yet, because we don't really know how far down the code we're going to go to complete the other direction of the branch, which is to say the case that a is not equal to 0. So this, as you can see, is a branch condition, branch type of instruction rather, and we are in location 0. And then the branch condition is codified to represent the fact that we're looking to see if a is equal to 0. Again, the address is not specified, and we're going to fill this out later. Next, we proceed to add 5 to ix. That is to say, now that we have written the micro instruction to branch out to a place when a is equal to 0, underneath this we're going to now place all the steps necessary, all the micro instructions needed to actually accomplish the addition of 5 to ix. So as I mentioned in class, in order to generate these constants like 5, we're going to have to use powers of 2 that are stored in the last I guess 10 locations or so of VESP's microstore. And the way that it is set up in this micro programming version of VESP is that the constants are read out into a location in memory, and that happens to be memory location 7, and that's where we shall find it once we complete the execution of what we call a microstore transfer instruction, which happens to be this instruction here. And that's the kind of instruction that is 1.1 just indicates here that we do have one of those micro store transfer instructions. Let me just again make a small correction here. microstore. All right. So now, and so after the branch microcode or micro instruction, we go and execute this microstore transfer instruction. And the choice that we make here is for read. We want to read the constant. And the constant 4 is actually stored in this location. This is determined by just noting the fact that if we had 0, 0 is stored in all ones, and then 1 is stored in all ones, but 1, and then 2 is stored in all ones up to here, and then to 1, 0, and then the next one becomes 0, 0. So that being the case, now we have 4 stored in location 7 in memory, that is in VESP's memory, and now we want to proceed from there forward. And of course our goal is to add this constant to 4, but as the structure, the bus structure of VESP puts IX and memory 7 both on the B bus, we need to handle this situation by moving one or the other operand onto the other side. So since this involves subtraction and we subtract B bus from the A bus, our preference would be to move IX to one of the registers on the A bus. And we will use A for this purpose. And as I emphasized in class, this is not certainly a good practice because A is a general purpose register in a way, and would be used by a programmer of VESP to perform computation. So when this happens internally and we get to destroy this register, of course, in the process, and that's not a good practice. And so a temp register would have been more appropriate, and there is space on the A bus to do that, but this is just an example. So we go and now move IX to A. So the next instruction that comes about, and then of course after that we need to do the subtraction, and these are actually described over here. So we have now a transfer type, data transfer type micro instruction here. It doesn't matter what the A bus is because we're moving something over the B bus, and that happens to be IX, so that this choice simply says select IX to the B bus, and then the functionality is to copy a B bus onto the O bus, and the destination happens to be A, so that's codified by 0, 0, 0, 0. The next thing that we do is to actually perform the subtraction, which we do here. Again, we pick A and IX, A and M7, the memory 7, into the B bus respectively, A bus and B bus. And then we perform a subtraction, and then we just return that to IX. These codes here that I've entered, they're all found in the 2 tables that I'm going to describe later in the slides in the presentation. But also we talked about this in class on Wednesday. And then the last thing that we do once we completed the operation is to set the red set to 0. Actually, red set to 1, not 0. So this will ensure that we get to return from this point back to where this operation was called from. Now, so this was basically if our condition had failed. That is to say, if A is not equal to 0, case has now been covered. So the other thing, of course, would be by this time we know that we've actually expanded 1, 2, 3, 4, 5 locations to generate this code. And then now we know what this address will be, because the next thing that we want to do is to actually treat the case where A is not equal to 0. A is actually equal to 0. this was the A is not equal to 0 case. So we go out and enter now the branch address, which is that location that we shall be at, which is down here, right here. And this is where we begin to handle the case when A is equal to 0. And in this case, we're going to subtract 4 from IX. So in order to do that, we're going to copy 4 by way of one of these micro store transfer instructions again. And it's a read in this case as well. And so this step completes that transfer of 4 into location 7 in memory, and that is best memory here. After that, we then copy M7 into A. That's what this code does. And since M7 is on B bus, it doesn't matter what we set A bus to. Typically, when we write triple X's, we take that to be 0 because it doesn't really matter what we enter in here. But we have to put something in order to write the hexadecimal equivalent of this, or in general, have to have something in there. And so we put a 0, 0, 0. That doesn't mean that we actually get to pick something on the A bus. It doesn't get used. That's all it means. There are times where we actually will enter 0, 0 for a purpose, but not in this case. So then we actually copy one more constant. This was not 4 but a 5. That's what we actually get to do when we do the addition. So now we have 4 in M7, which was copied into A, and then 1 in M7 now. So we go out and add M7 to A, which is what this operation is. This time we actually put something both on A bus and B bus. And now we do the addition. And by this time, A actually happens to have 5 in it. And then the next thing that we do is to add IX to A, and then again set the red set to 1. This is just a little mistake here. And that completes our code. This is really what we have by way of microcode to accomplish this conditional statement that we had earlier. So now this is the hexadecimal version of the same code, and I've just taken these numbers that are in binary patterns here form and then wrote them as hexadecimal numbers. Now the reason that you want to do this is if I were to put this into VESP source code, the micro program version, I need to enter them in C, and this would be the way to do it. And I'll just simply prefix each of these numbers by 0x to specify the data type for this in C, and that will take care of that. Seems like I've just copied these. Correct these. So red set is equal to 1. Red set is equal to 1. So this really takes care of the hexadecimal code. And we talked about these in class. So what this really does, this table, it just allows you to quickly enter the codes into the two fields that you would need to specify for data transfer operations. Now, these codes, I actually rechecked these and they're correct. And I guess the point that needs to be made here is that there are 8 bits for when we look at the data transfer operation. Let's actually go ahead and look at one of those. For example, here we get to have 8 bits up to here, and then 8 bits from this point down. Now, if you look at the left-hand side of this white line, you'll see that 6 of those 8 bits are consumed by A bus and B bus. This is true for any micro data transfer operation. And now the 6 bits over here are always prefixed by 00 in the case that we have a data transfer micro instruction. So what then happens is that you take these 2 0 bits and combine them with these 2 0 bits, which simply in this case will be like 0 followed by 5. So in some cases, this bit, for example, may be 1, in which case you get to have, in this situation, constant 13 that will be D in hexadecimal. But these bits will still be 0 in that case. Of course, when you get this bit to be 1, this could also be something other than 0. And of course, this could also be 1 here, this bit, in which case this would be as large as, if you look at it here, 2. And if both these bits are 1, then you go to 3. So the maximum you can reach here would be 3. And then, of course, these bits could go up to 15 if need be. Now, not all of these cases are specified, but if you look at here, you would see that there are situations here, like if you look at the different entries on the A bus, the first digit may go up to 3. And likewise, the second digit may go up to F. And so starts out here, and then it goes up to 0 to 07, 8, 9, and so on. And this pattern will repeat as we go between different values of the leftmost hexadecimal digit. Like here it's 0, here it's 1, here it's 2, here's 3, and in every 2 rows we skip the 16 different values of the rightmost 4 bits in hexadecimal arise. So this really is how that is. The other 8 bits are always going to be taken as such and chunked into 4 hexadecimal digits. So these representations here in 2 hexadecimal digits basically always collect these 4 bits. So it's a little easier to decode those or encode them if you like, because the first 4 bits are for the function select, and then the second 4 bits are for the destination select. So this is basically how these tables are to be interpreted. And before I go on to the summary, what I'd like to do is to quickly talk about the source code here, so that I get to point out a few things to you about the thing that needs to be done. Now, the microcode that is written in here, which is really the initialization step here, the load microstore function does take care of all the initializations in the microprogram version of VESP. But what needs to be said here is that there is a machine layer here, which sits atop over the micro layer. So all of these codes that I'm actually scanning through here, they are related to microcode. But the these calls that are taking place here in the execute routine, for example, that I allow myself to visualize or view at the end of the execution, is to activate the micro program that needs to be executed for any one of these instructions that we want to perform. For example, this one activates the add, and there is an address which we specified in the microstore, as you just saw. As we scan this down, you will see it again. That address was initialized here, like location 5, and that is where the microcode for add begins, right here. Location 5 right there, as you can see. Every one of these instructions happens to have a location in the microstore, the machine instructions, where a microstore where the microcode for that particular machine instruction begins. So these particular calls just enable that. Of course, this execution process is activated by way of determining the instructions content, and we do this, of course, by looking at the leftmost 4 bits of IR by shifting it 12 bits to the right. That's what we end up doing here. So that's how we really get to know what instruction it is. This is where the control is kind of passed from the machine layer. This is exactly where it happens to the micro layer. Because as you can see, what we're doing here, we're really checking to see what the IR's opcode is, what the opcode field contains. And that triggers or kicks in the exact microcode that needs to be executed. So this is where the interface between the machine and the micro layers of the VESP is located. And decode, of course, is something that we don't get to do much. All we just do is identify what instruction it is. That still remains something that happens in the machine layer, because there's nothing that we really get to do, just display that we are doing one of those 16 instructions. So effectively, this is really what takes place. The main cycle proceeds on to, as before, decode and the fetch, rather, decode and execute steps. You see them right here. Main cycle, fetch, decode, execute. And those steps are then accomplished by way of calls to the in the execution step, as well as in the fetch step. Also, fetch step requires operations that would change certain registers like MAR and so on, NIR, and that also happens in this particular location. And the fetch address for this is 0. That's where we begin all of our operations. If you just look back here again, fetch is located at 0, and that's what this first microcode is all about. This is what we do here to fetch. So I think this is about it. Just wanted to make sure that you understand how this happens. And the main loop, basically, over here is pretty much the same. Not much really has changed. We go to the main cycle, and if it's an execution, otherwise we that is in this case, I guess. But it's the main cycle, which is our machine cycle, which then is further decoded and executed by the microcode, which is really what happens here, the main cycle. We always get down to here. So we execute the same process as a source code here. The machine cycle gets executed, but what happens, of course, in the process is machine cycle is further expanded into microcycles, micro level cycles, and that gets to be also codified. And so, of course, there's also one other thing that we get to do in the initialization process. I assume it's right down here somewhere. We do have an initialization process which creates all the bit patterns in the microstore. Without that, of course, the machine would not know what to do. So we did run an example in class. Maybe I could just, if I could really fire this up, it can, executes. Otherwise, I'll just leave this alone. Seems like the build succeeded, and we're here. So as you can see, that everything has been loaded. All the instructions have been stored in the micro store as microcodes, and now we could enter a program and execute. So we just put 0 to enter a program, and then we write it here, a starting address of 3, and then we want to type the program ourselves. So we just write our typical program, put something into A, something like maybe 6, something into B, something like maybe 7, and then add the 2, and then halt, and then put -1, and we just continue. And so this shows us what program we have. Let's just go ahead and execute this. Let's see what happens. So for a machine trace and micro trace, you want to see the micro trace, you want to press 1. So this really shows you what happens, like all the way from the top. You see the machine cycle first, and then you see the MIR register, which is the micro instruction register here, and you see exactly what instructions are executed. Because the first bunch of micro instructions would be to fetch, and after that you will have, once that it gets done, you will see that the fetch is completed here. The decode, there's nothing you do in this decode process, as I said earlier. And then execute, of course, involves another bunch of micro instructions execution. So this continues all the way to the end, where the last instruction that we execute is halt, which is where things end. And halt instruction is only 2 micro instructions long. So here's a machine instruction that is executed by way of 2 micro instructions. I guess that probably is sufficient for you to proceed from here. One thing that I want to maybe quickly mention is if you go back here for a second, you are asked to extend the instruction repertoire of VESP. And so what you need to do is to add some more instructions, which then means that you're going to have the fetch and execute, decode and execute steps rather, expanded here when you add new instructions. So I can quickly get there. You're going to have new instructions. That means you're going to have to modify this. You're going to have 2 more instructions or 3 more instructions, and you're instructed in the homework, which I'm going to talk about briefly, how to proceed with this. And not only you're going to change the decode, but also you're going to have to add the same 3 instructions in here. That means you're going to have to put more cases in here. There are only 16 instructions here. You're going to end up doing more than 16. And if I go back to the PowerPoint presentation, I'm not sure if it's actually there. It seems like I have, yeah. So I entered the homework assignment in here, and you see that 3 more instructions, as a matter of fact, 4 instructions, not 3, have been added. They've been given their opcodes. Actually, you kind of expand the add instructions opcode into 4 bits, and that means that you're going to have to borrow another bit after the first 3 bits of the instruction register. As a matter of fact, it looks like you're going to have 2 bits because you go up to 3, and those are the 4 instructions that the homework assignment asks you to incorporate into the source code. So 2 places you have to work on, and the machine layer would be decode and execute. And then you need to then, of course, in the execution process, specify a microcode for each of these 4 instructions, and then determine the locations where they're going to end up being at. And those locations then will have to be initialized as we've done for the other instructions, so that you can actually make the calls from the execute function in the source code. Once you complete this, you're then asked to write a simple program to test your instructions to see if they actually work. And since we already know that add works, we just get to test the other 3 instructions in here. Okay, so this is really all we did. This is something that we were able to go over last week, and so I'm going to now conclude this presentation, and we'll start a fresh week this week with possibly kernels and how we get to work on kernels using VESP architecture. So until I see you in class today, take care.